Welcome to Tier 3 Chemistry. My name is Anna Simmelson. This video is the first in the series that will be dealing with acid-base reactions as it applies to organic chemistry. So basically, this video can also be called Everything You Always Wanted to Know About the pKa but Were Afraid to Ask. So the concept of acid-base reactions is very important to an organic chemist. And the question that we organic chemists are concerned with is, say we want to remove an acidic proton. The question is, the base that we chose to do the job, is it strong enough to remove this proton? So as an example of this, I chose the reaction of alcohol with ammonia. And the question that is commonly asked on the organic chemistry exam is, will equilibrium favor the products? Or another flavor of this question is ammonia strong enough to deprotonate alcohol? Now, notice that I wrote pKa value underneath alcohol on the left-hand side and underneath ammonium cation, which by the way is missing the plus charge, sorry, on the right-hand side. So why did I choose these particular species? Well, if we look at the left-hand side of our reaction and we recall the definition of acid according to Bronsted-Lowry, it tells us that acid is a proton donor. So between alcohol and ammonia, we can see that alcohol actually donated proton to ammonia. So alcohol in this scenario is an acid, and it has a pKa of 16. Now, if we look on the right-hand side, then in this regard, ammonium cation would be donating proton to the alkoxide ion. So in this case, ammonium is an acid. Now, the rule of thumb is the following. Equilibrium favors the side with a weaker acid. Now recall that the larger the pKa value, the weaker the acid. So in this particular example, equilibrium will favor reactants, not products. In other words, ammonia is not strong enough to deprotonate alcohol. But you might ask me, well, how do you know that? We will actually calculate the equilibrium constant for this particular reaction. And this will clearly demonstrate that indeed equilibrium favors reactants and not the products. So let's calculate the equilibrium constant for this process. Now recall that equilibrium constant is concentration of products over concentration of reactants. Now if this equilibrium constant is greater than 1, then equilibrium favors products. If equilibrium constant is less than 1, equilibrium favors reactants. So let's see how we can use the pKa to calculate this value. So let's first look at alcohol and its reaction with water, where alcohol is acting as an acid. This would produce, again, familiar already alkoxide ion and hydronium ion. So if we look at our Ka for this process, let's call it Ka1. This would be RO minus times H3O plus divided by concentration of alcohol. And notice that water is not included. If you're still not clear as to why water is not included, it would be a good idea to review the equilibrium chapter in your general chemistry text. And this whole thing is equal to 10 to the negative 16. Now notice that what we're interested in is the ratio of alkoxide to alcohol, which we can easily express from here. We can then say that, let me just scroll down a little bit so we have more space. We can then say that RO minus over ROH, alkoxide over alcohol, is equal to Ka1 divided by concentration of hydronium. Okay? All right. And so now let's look at ammonium cation when it's also acting as an acid. So actually, let me scroll down, and I think it would be easier if I do it in this part of the screen. Ammonium cation, NH4+, is reacting with water, right? Donating a proton, like a good acid should, producing ammonia, NH3, and hydronium ion. So then for this process, Ka, which we will call Ka2, is equal to concentration of ammonia times concentration of H3O plus divided by concentration of NH4 plus cation. And this value is equal to 10 to the negative 9. Now, if we go back to our original equilibrium constant, we are interested in the ratio of ammonium cation to ammonia. And we can extract it from our Ka2. In fact, NH4 plus divided by concentration of NH3 is equal to hydronium concentration over Ka2. So now we can plug in these values into our original equilibrium constant. In other words, we can say that this whole thing is equal to Ka1 over hydronium times hydronium over Ka2. The hydroniums cancel, and now it's ratio of Ka1 over Ka2. 10 to the minus 16 over 10 to the minus 9. This will give you a value of 10 to the negative 7, which is less than 1. So we know that equilibrium favors left-hand side. It favors reactants. Now, this approach can be used to calculate the equilibrium constants of all acid-base reactions, provided that you know the pKa. Just remember that the equilibrium constant is Ka1, in other words, Ka on the left-hand side, over Ka2. And by doing this mathematical operation, you can see that if these numbers were inversed, the equilibrium constant would be much greater.